So good morning, everyone. So before lunch, I'll try to make it quick. So I'm going to update the biochemical structure study of the holoenzyme complex, and celebrating the new milestone of the foundation. Yeah, absolutely. That's great. So this is studies for our patient family. So the major goal of study to understand the structure and the shape of the whole enzyme at atomic detail, so we can learn how the mutations can change the positions of atoms and amino acids in the whole enzyme. So hoping that using those atomic structure, they can facilitate designing chemical therapeutic that can specifically restore the mutant holoenzyme back to its normal shape, by which we're hoping to restore its normal function. In the structural biology word, in brief, this structure dictates the function. So we really want to restore the structure of the mutation. But of course, there's the challenges we're facing. But there's some of the very general challenge for high resolution structure determination. If the protein needs to breathe or even do gymnastics to execute the biological process, it's not like a rock. If a rock cannot execute any processes, so it have to be dynamic, and but that gives a challenge. And the B prime delta holoenzyme turns out breathes at very high level, and so that's give a challenge. So right now we're using 8 different strategies try to overcome those challenge and to determine the atomic structure. I'll show in detail. So one thing, we do collect, the one data set with 1,500 micrographs. So we use so if we compare, one way to look at it, so we use Relying, which is a GPU-enabled program to process all the micrographs. This is just a very peak, like a 3,000 randomly picked for B prime and delta holoenzyme. And this is a different complex with more defined conformation. And you can see 5,000 randomly picked particle, you can get a very good 2D classification. So one way to get a high resolution structure is we get, because single particle image, the resolution is not high enough. You have to be able to average a large number of particles in the same shape and to be able to get high resolution. And for 2D projection, and then to reconstitute the 3D structure. So this is a challenge for B prime delta. But one thing is, it's not simply because it's dynamic, also because the artificial intelligence is not very good into the 2D class average for this complex from Relying program. If we do manual picking, we can start to see the shape of the particle just by manually pick the one by eyes. But of course, which is impossible to do all the data processing with the. So that means it may be the globular shape of the complex to really challenge the artificial intelligence for 2D classification. So with that, another program that performs better, which is a system. And so if you randomly pick 6,000 particles, and there's some classes I highlighted here start to show very reasonable 2D class average. And so with that, however, we're still waiting for a system, the new version. They complement with the phase correction, because the data was collected with phase plate. So we really need to wait for that to process the entire data set. This is 1,500 micrographs. But even with that, we predict that we may not get high resolution structure. We're thinking maybe get 10 to 20 angstrom resolution. That's best hope for the current data sets. We do, and data processing might be slower because the system Relying is not, GPU enabled. So which is but our target is really to get 1 to 4 angstrom resolution structure. That's our target, and to be able to use for our goal. So we do, besides computational strategies, we're trying to explore, but we're exploring a wide variety of biochemical strategies. And there's 7 different strategies we're trying, biochemical strategy we're trying now. The overall goal is to add shape features that can facilitate artificial intelligence, 2D classification, and also assemble larger complexes with more defined conformation, meaning that they reduce the gymnastic of the complex, so we can capture the most representative conformation of the complex. So by doing that, for example, we do select antibody from a semi-sensitive Fab library, but we fail to identify the high binding affinity Fab that directly bind to the whole enzyme while we're waiting for Brian's nanobody. So hoping we can get more information from there. For N-termini, we do have a 3 truncated construct. The shorted construct appear to work well. And here's data. But by secondary structure prediction, the N-termini are largely disordered. So, to reduce the flexibility, so we're trying to do different truncations, and they all work well in the single protein test, and the holoenzyme can also form readily well. So those could be potentially used for a cryo-EM study. Another important dynamic portion for PB2A is highly unique is that the catalytic subunit is highly dynamic. If you look at the internal packing interface, there's a improper packing. So those residues introduce imperfect packing between the two central beta sheets, and that can cause, when you lose metal binding, and it causes a large shift in the central beta sheet, and that can lead to recycling of the whole enzyme. But this is kind of unique for the PP2A catalytic subunit. But in the active conformation, so all the PPP family have almost identical structure. So we're trying to introduce mutations at the two locations that create imperfect packing. And so hopefully we can, so those mutants, we made it and that they express very well. And we're trying to make a double mutations, combine the different mutations and to make it further improve the internal packing of the catalytic subunit. So also, try to use a different interacting proteins that increase the size to facilitate cryo-EM study, and particularly by interacting with the binding partner. So a lot of protein assembly, functional assembly inside the cell, they have more defined conformation rather than the individual, smaller complex. And so one thing we're trying to do, combine with the idea, to understand how holoenzyme, whether the mutants can be preferentially decommissioned, for example, besides the holoenzyme recycling, there are PP2A inhibitory protein like CYP2A and the SET, and those are important PP2A inhibitory protein that are implicated in cancer, and we think about, they might be reasonable to look at in the neurological disorder as well. And the other interacting protein identified by Wolf, I think they are important in target to explore. But for CYP2A, Brian, they've been discussing, was suggested to inhibit B prime delta holoenzyme in glucose metabolism. So that's a good target to test. And for SET interaction, the Ito in the lab, he has demonstrated that, the SET specifically interact with the A beta subunit rather than A alpha. So A beta, that's constitute 15% of the total A subunit in the human proteome, so might also be a reasonable target to look at. So for CYP2A, for example, and we made different constructs, and this shorter construct cannot interact poorly with the B prime delta holoenzyme, but this longer construct works really well. So we're trying to we will measure the binding affinity and test the particle by cryo-EM. So for SET, we do look at, by pull-down assay, seems like you do see interaction with the B prime delta holoenzyme, and in the holoenzyme in the A beta version, and but one thing what we need to do is to make the A beta form in insect cell test binding with our GST tag, and in another study, demonstrated that in B prime gamma, if you use a GST tag, the binding is weaker than removing the GST tag. So you can get much, the better binding without, so we can try to, to improve that. One thing is interesting about this inhibitory protein. There is a drug, FTY720, which Yitung participated in this work, has shown that it was suggested that to disassemble the set, which is our oligomer. If you disassemble the complex, you might alleviate the inhibition of the whole enzyme by by the complex, by the set. So in that regard, so presumably we can test how ID mutations, can affect the set interaction with the whole enzyme where there's more prone. And with that, we can, use as a tool for cryo-EM study of the mutant holoenzymes, and also presumably to see whether FTY720 could reverse that inhibition of the ID mutation. So that's something might be interesting to test. Another thing, strategies use a structural tag, which is an interesting idea. The reason being, so some helical structure tag, if you put engineer to the upper helical structure of the A subunit, and then one of the tag will acquire these tools and start to engineer this kind of a complex. As you can see, the complex is less globular anymore, and you add a lot more feature to the complex, so that could facilitate 2D class average in cryo-EM study. And so we can put in different location and see how that can be helpful. One thing is interesting, this Fab against this helical structural tag that give a nanomolar binding affinity. It's a very tight binding, and we're hoping that could be extremely useful. And another tag where engineering is the MBP tag. MBP can also generate easily identify Fab, that could be facilitate the cryo-EM study as well. So another important, cross-linking, chemical crosslink, because, as we mentioned, for B prime delta holoenzyme have a C-terminal extension, and they might dictate charge interaction with the core part of the base B prime subunits. And in some level, although it may breeze out, open up the conformation you're breathing, and that introduce the heterogeneity of the particle. So by that, because some chemical cross-linking linker carbon diimide, and they tend to cross-link the positive charge residue to the negative charge residues with zero-length linker. So we use this kind of chemical cross-link, to facilitate, the stabilize the conformation, trap the conformation for a cryo-EM study. And in some certain conditions, you can see really well cross-link between A subunit and B prime data, so we can, see whether we can incorporate. But in brief, so we want to combine these different strategies to really nail down the structure. And but there's a lot of all promising particles, validated biochemically, will be examined by cryo-EM. So we're going to let the data to speak, because the major data the major key the success is for high resolution structure determination is the performance, the good performance, automatic 2D classification. So we're going to see, process a different data set, different particles, and see which one give the best performance. And we're going to pursue that in large data sets. So that's essentially, I cover AIM3, the major goal, to look at, determine the cryo-EM structure. Hopefully, whereby all these strategies, we can nail the structure. The AIM2, we do want to look at, whether the ID mutation give you aberrant substrate recognition, and although by bioinformatic analysis, there's thousands of substrates are predicted for B prime family, and one draw attention is a crab. Richard is also, looking at that, which is extremely interesting. We do measure, the titration of the Crab phosphopeptide, and with that we measure the KCAT and KM value, and and look at the ratio, see how they change. What's interesting is although we think the C-terminal extension of B prime can have autoinhibition, but by chemical assay, we didn't see much inhibition. Compared with the B prime gamma 1 holoenzyme, it's the activity is only slightly reduced, but the mutation really reduced the activity. But of course, we didn't examine for 20 mutation. But what the key here is to understand the biochemical code, to look at global changes, prediction for all the potential substrates. And what's interesting, the literacy, reduce the phosphorylation of crab, but by this data will predict they have hyperphosphorylation. But however, AKT, they have a negative feedback load, so we really need to look at, how different substrates talk to each other. So biochemical data need to incorporate into the signaling network to understand the biology. So that's what we want to do. But one thing is important to, besides the mutation, the different substrates, there could be also recognition of aberrant substrates. And that's another thing, one need to check by determining the biochemical codes. The one thing, because you have this mutation here, negative, but there's a lot of positive charge residue, so the mutation might not have a significant impact. And also, if you have a longer distance, so this here have very short linker, so if you have longer distance, more dependent on the charge, and so that will give you more strong phenotype. So that's by using this, we're going to change the charge distribution surrounding the phosphorylation sites that may affect the mutant, how mutant affects substrate entry, whether you can have recognized aberrant substrates. So by doing that, we can probably use this kind of data to look at, bioinformatically, what aberrant substrates could be potentially recognized. Of course, we need a variance distance. That's the next step, to look at how they get changed. Aim one of the study, we're trying, the idea is whether the ID mutation can cause increased decommissioning of the whole enzyme. One step of decommission is a PME1 mediated demethylation of the whole enzyme. So for full-length, since there are B prime data have a C-terminal extension, and that that might provide autoinhibition domain. We think this autoinhibition might suppress PME1 binding. So PME1 binding to the active site also involves substrate binding motifs. They block substrate interaction. And however, if you have the C-terminal extension in B prime delta, you will block a PME1 interaction and block recycling. But ID mutation, they could be potentially, increase the interaction if you create open conformation. And that's, compare, the B prime delta whole enzyme, its interaction with the PME1, compare with the B prime gamma 1, you can see there's a stoichiometric migration of PME1 with the B prime gamma 1 whole enzyme. However, this is drastically reduced in B prime delta whole enzyme. So we try to look at, the mutations. And you do see increased interaction. For example, this is the B prime delta with the E197K. And their data here is not that great, but we do see some increased interaction for 198K and P201R and the B prime delta, 207R. So we do need to make more mutations and to examine how they change the interaction. But by quantification, so if you B prime gamma 1, we see like 100% stoichiometry between PME1 and PB2AC, and the B prime delta whole wild type, you see, they reduced to around 30%, and there's some increase, by the mutation. So they are higher, but not really completely comparable to B prime gamma 1. But even that, I think one thing we really need to examine basal phosphorylation level of purified B prime delta from insect cell. That be potential to cause the basal activation of B prime delta whole enzyme. So we need Bryan's antibody again. So the idea tested here essentially, so if you have ID mutations, and now you tend to open up the conformation more, so the whole enzyme breeds a lot more dynamic, and the PME1 have a chance to come in and they bind to the mutant whole enzyme. So with that, I think I'd like to wrap up. The people who did the work, I mentioned Yitong and a few times. Whenever I didn't mention Chengguo already involved, so by default. And so Annie, they have been in the lab for quite a while. But there are other lab members. This picture is also Kasia and Wilson. There are new lab members. They really contribute. Also, Kasia contribute quite a lot, and Wilson start to contribute. Ken, they is also important of our team. Thank you very much. Appreciate any questions. Yes.
Yongna, one of your slides actually showed the impact in the 4 different mutations was all pretty consistent. Is that what you would expect?
You mean the in phosphatase activity or PME1 binding? There are variations virtually. It's not identical. There are some like this one have. We really need to repeat the data in some way. We think that there's a lot of different factors come together. Like one thing we haven't tested is recycling with TPO. TPO alpha 4. That's what we really need to test. So there, and also how different whole enzyme, they have different stability. And by this is just the one aspect, the phosphatase activity.
When you look at that, though, you've got, so the first time we've seen 4 different variants, all sort of consistently, when you compare it to the wild type, I guess, is that what you expected?
Yeah, we're expecting this. They all have a reduced activity. We are expecting this. But the key, we need to look at globally in human proteome based on what the data acquired here. Yes, sir.
Is that purified whole enzyme there in these assays?
Oh, yeah. They are purified whole enzyme, quantified the amount in the assay. Yes?
I have one remark. So it's going to be a challenge to crystallize this whole enzyme because it is so dynamic because of the N and the C terminal. So I think that maybe if one of your strategies to stabilize that is to cut off the N terminals.
But we will. That's one thing. That's one thing is important. I think for all the construct we made, we're trying to generate as many biochemical assays as possible. We've tried to validate all the construct, use all the assays we're trying to. So the goal is if your truncations have to be comparable to wild type full length. The mutation, we don't create anything there like a mutant, ID mutant behavior. We don't want that. In terms of the mutant, I think in several scenarios, a lot like a SAD4, sorry, SAD interacting protein. We want to see whether there is a ID mutation have more prompt, so they can help to. Yeah, but we definitely will keep that in mind. We're going to test all the particles. If a full length give a good 2D class average, we will stick with the full length. Currently, based on the structural modeling, by prediction, C-termini is more important. That's why we don't truncate C-termini at all. But N-termini, we definitely want to keep a different variance. to see. One way we try to produce is a FRED sensor, and to see, whether if you have truncation and termini, the FRED sensor can accurately predict the effect of ID mutation. So that's another criteria we use to to evaluate the particles.